Lutgens and welcome. For today, we are going to discuss about plate tectonics. So, uh, before the unifying theory of plate tectonics, there was only the continental drift proposed by Alfred Wegener. The continental drift hypothesis stated that the continents had once been joined to form a single supercontinent. Wegener proposed that the supercontinent Pangaea began to break apart approximately 200 million years ago and formed the present landmass. So this was the breakup of Pangaea from 250 million years ago. The division of from Pangaea and which were divided eventually to Laurasia and Gondwana land. Um, Laurasia is composed of our northern hemisphere present day northern hemisphere continents, and Gondwana land is composed of our southern hemisphere continents plus India, in the India, and then by 100 million years ago, both Gondwanaland and Laurasia were rifting away from each other. They split up the both continents were split apart into different pieces, and eventually towards the present day situation as of today. Okay, so it was an idea before time. His basis was the matching continental puzzle, wherein some parts of the some parts of your continents can fit to another parts of another continent. So, for example, Australia can fit on some parts of um, uh, Antarctica, and then the in present day Brazil once fitted somewhere in eastern in sorry in western in the western portion of Africa. And also we have the rock types and structures which matches in both continents, like for example the if I'm not mistaken, the Appalachian Mountains, which has a continuous mountain range toward up to Europe. Okay, and then yeah, and also your ancient climates, wherein the fossils based on the fossils of your uh, of your flora and fauna did not really match the present day climate, um, wherein uh, it also matched the different fossils over there with the same problem of climatology. Okay. Uh, okay. So there's the Appalachian and Caledonian mountain ranges, which were theorized uh, to be the same mountain range as each other back then in the time of Pangaea, and then the glacier evidence, wherein there was once a glaciers that were flowing towards parts of South Africa, the the southern portions of South America, and India, and also your Australia. However, uh, the idea of the continental drift theory was rejected because Wegener cannot provide a good explanation on how it led up into 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 that idea of continental drift. Basically, history says that Wegener proposed that the movement of the continents was due to meteorological and the effects of waves of the seas during storms. During storms, your continents are pushed towards their present day movement, uh, and that was not really, and still today that is not really a good reasoning towards the continental drift theory. However, his theory and um, uh, next to the next few years was uh, given a second chance by different scientists. Okay, so later in this part we will be explaining about that. Okay. So according to the plate tectonics theory, the uppermost mantle, along with the overlying crust, behaves like a strong rigid layer. This layer is known as the lithosphere, and a plate, by definition, is one of the numerous rigid sections of the lithosphere that moves as a unit over the material of the asthenosphere. So basically, the asthenosphere is somewhat carrying the lithosphere, and we will be relating that um, to a uh, conveyor belt later on. So first we have to define the types of plate boundaries and how were they discovered. So first we have the divergent boundaries, also called the spreading centers. These are the places where the two plates are moving apart, and then we have the convergent boundaries uh, where two plates are actually moving towards each other. And we have the transform fault boundaries, which are where two plates are sliding or grinding past each other without producing the or reduction of uh, your lithosphere. So that is how it is it is shown. So first we have the divergent boundaries. So these are composed of oceanic ridges and is great seafloor spreading. We have the oceanic ridges, which are continuous elevated zones on the ocean floor. Of all the major ocean basins, the rifts at the crest of the ridges represents the divergent plate boundaries. And we have also rift valleys, which are deep faulted structures found along the axis of divergent plate boundaries. Basically, they are just baby or somewhat a younger version of your divergent boundaries, and your oceanic boundaries are very much well developed. And your seafloor spreading is the phenomenon that or the other theory for your plate tectonics. The seafloor spreading hypothesis is a composition of your plate tectonics. Okay, so this is how it happens. First, we have a continental crust or two continental crusts that are being uh, starts with a warping and splitting away from each other. Then early on we have a rift valley. Okay, so this is where mantle material is exiting, and then we have your linear seas, and eventually your oceanic ridge. That if you can see it while using your Google Earth, where if you go to uh, somewhere in between in the uh, in the middle of the Atlantic Ocean, you can see that going towards Iceland. Yeah. And for rift valleys, you can also see that in the Horn of Africa and also into Iceland. Yeah. And then linear seas, you can see that in the Red Sea. Yeah, it's linear, it's pointed, and it's a divergent boundary. It's dividing your uh, Arabian plate and your African plate. Okay, so and then your continental rifts. When spreading centers develop within a continent, the landmass may split into two or more smaller segments, forming a rift. and that is what is happening in the East African Rift Valley. And then we have the convergent boundary, which occurs when one oceanic plate is forced down into the mantle beneath the second plate. So there are actually three types of convergent boundaries. We have the oceanic continental, wherein the oceanic and the continental is converging towards each other, wherein the denser oceanic slab sinks towards the asthenosphere. It is always that the oceanic slab sinks because the continental slab is too light and too buoyant for it to subduct. And then because of the subduction and the friction in between uh, the two uh, crust or lithosphere grinding past one grinding below each other, and the heat from the mantle slowly melting the subducting oceanic crust, there is some parts of the melt that rises up, and it forms your continental volcanic arcs, which forms in part of your volcanic activity caused by the subduction of the ocean. And then these examples includes the Andes Mountains, the Cascades, and the Sierra Nevadas. Okay, so mostly the Andes Mountains is in Chile, in South America. So this is how it happens. So we have the subducting oceanic crust, the friction uh, of the subducting oceanic crust, the surface in between them and the continental crust, and also your solid mantle, and the heat coming from the mantle melts the subducting oceanic crust, oceanic lithosphere, and eventually, since the melt is hot and buoyant, uh, it well, the basics of uh, materials between different temperatures and pressures of materials, um, the hotter and light materials goes up, and the dense cold materials goes down, and eventually your melted materials will be forming your volcanoes. And then we have here the oceanic convergent boundaries, where two oceanic slabs converge and one descends beneath the other. And these kinds often forms your volcanoes on your oceanic floor. So volcanic island arcs, it's the same concept as the your continental volcanic arcs, but instead with your oceanic continental convergence, but instead it forms volcanic islands from the sea. So we have examples: Aleutian, Marianas Islands, Tonga Islands, and also the Philippine Islands. So same concept. We have the subducting oceanic lithosphere, the other oceanic lithosphere that is overriding, and then the melt from the subduction going up, and it forms your volcanic island arc. And the third type of your convergent boundary is the continental convergence, where two continental plates are colliding. Since none of them can be subducted, they will be colliding instead. So this usually forms huge mountain ranges and large bodies of deformations. For example, your Himalayas and your European Alps in, of course, in Europe. So this is a good example. So in the situation of the Himalayas, it is actually the Indo-Australian plate. Basically, it's the India part, and also your Eurasian plate that is colliding towards each other. Okay, so this subducted part, was the former oceanic lithosphere that was subducted during its time before the continental portion and the portion uh, collided with each other.